Alright guys, now that we know how to calculate Riemann sums with area underneath the curves, this time we're going to do a problem that doesn't give us a table. Okay? When it doesn't give us a table and only explicitly gives us an equation, we have to, in a sense, create the table and then be able to quickly get the graph from that. So we have an x squared plus 1 graph, which looks like a parabola shifted up 1 unit. And we're going to go from 0 to 2. So we're going to go from 0, okay, which f of 0, if this is my function, would equal 1. Okay, so we have 0, 1. And then we're going to look at what the y value would be at 2. Okay, so here's 1. We could say here's 2. So what is f of 2? Well, plugged in there, it would give us 5. So 0, 1, and 2, 5. Not really much drawn to scale. And let's get one more point just for good measure. We have 1, 2. So 1, 2, 3, 4, so on and so forth. Not really drawn to scale, but I'm able to show you that we're trying to estimate the area bounded by the graph and the x-axis, which in this case, if I drew a straight line down from the graph, we're looking to approximate. Okay, so we're approximating this area right here. Now we are going to use Riemann sums, and I'm only going to really draw the graph for this first one, and then we can modify it to answer the other parts. We're going to start with the left Riemann sum though. Okay, so they're equal subintervals, and there's 4 of them. So there are 4 equal rectangles. And when I say that they're equal subintervals, I'm only talking about that their widths are equal. Now there is an equation, delta x is equal to b minus a over however many rectangles that you're looking for. So we're going to say over n. So we could say the width of these rectangles over here that I highlighted in blue will equal, interpret this as from 0 to 2. Okay, you've done this with intermediate value theorem, so on and so forth. Mean value theorem, this is going to be your first x value and your second x value, otherwise a and b. So we'll say the high minus the low. Over in this case, we have 4 subintervals. Okay, we're looking for 4 rectangles. So each width is going to be 1/2, which makes sense, because to fit 4 rectangles from 0 to 2, I need to have each width to be 1/2. So I'm going to go from here, and again, we're looking at left Riemann sums. So there's a rectangle's width, here's another one, here's the third one, and then here's the 4th one here. Okay, and because we're doing left Riemann sums, the top left corners of these rectangles that I'm about to draw will be what hits the graph here, 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 and in this case, right there. Alright, so let's go ahead and go straight to the right, down. Straight to the right, down, and then fill that in. Straight to the right, down, fill that in. Straight to the right, down, and fill this in. This is going to be the left Riemann sum, which for this function, if you say this function f of x is increasing, and you can see f of x is concave up, these are the stipulations excuse me, that will show an under approximation. And you can see that verified with the actual picture. There's a lot of the graph that does not get accounted for, all here, here, and here. And how do you do your per justification and all that? Is right here. It's going to be an under approximation because, or per, it's best to say because, f of x is increasing and f of x is concave up. Okay? So let's go ahead and calculate this. It's going to be left sub 4. They're equal subintervals of 1/2. And all I have to do is find what are these left 1, 2, 3, 4 heights. 1, 2, 3, 4 heights. That's what I'm looking for. Okay? Which 1, 2, 3, they will go right there. So let's go ahead and calculate the first one. again, my biggest suggestion to you is to create the table rather than having all these f of whatevers all over the place. I only did that for visualization purposes to get the graph going, but ultimately what I would want you to do is see that you're going to create 4 subintervals, so you need 5 points. It's always one more than what the number of subintervals that you are looking for. So we have x, y. We calculated from this equation that the width is going to be 1/2. So starting at 1, we'll have 0.5, then 1, then 1.5, and then we would have 2. Otherwise, your rectangles are going to look, these rectangles that I showed you right here are going to match up right. 1, 2, 3, 4. Okay, and they're just touching because we're going to find the area with no gaps. Okay. All right, so we need f of 0. So a quick way that you can do this is what we have in our calculator. Let's go ahead and clear that line and press menu 1-4 to clear all storage, menu 1-5 to get a nice clear blank canvas. Okay, so x squared plus 1 is my equation, and I'm going to store that as f of x. Okay, and yes, this is a better alternative than using the table, the independent variable ask, and all that stuff. And all I'm going to look for is what is the value going to be of f of 0, f of 0.5, f of 1, f of 1.5, and f of 2. What do they yield as far as my answers go? So f of 0 gave me that, f of 0.5, f of 1, f of 1.5, and f of 2. Alright, so we have, let me see if there are more decimal places. Nope. So 1, 2.5, whoops, let me go back. 1.25, 1.25, then 2, then 3.25, and then 5. Okay? Now don't think that there's like a special kind of jump. This is not a line. This is not a linear function. So these jumps are not going to be the same. You see this first one is 0.25, then 0.75. You know what I mean? And then what? This is 1.7 or 1.25. Like, don't look for a pattern on this, and then this is going to be 1.75. Okay? Don't look for a pattern per se on that. Just know that you're looking for those y values that I just filled in. 1, 1.25, 2, 3.25, and 5. Okay? So if those are the y values, we want to do the left Riemann sum. So I'm going to pick up the pace just a little bit. That means these 4 numbers here, otherwise 1, 1.25, 2, and 3.25. Those will go here. And then that will give you your approximation. Okay? Let's go ahead and put that into our calculator. So we have 1 plus 1.25 and 2 plus oops, let me clear this. So 1 plus 1.25 plus 2 plus 3.25. Okay? Plus 3.25. And that's going to be multiplied with our delta x of 0.5. Remember, we GCF that out, so we just have to do it one time. And we get 3.75. Let's see if there are any more decimals. Nope, that's it. Okay, so 3.75. There are no units of measure on this. Okay, so we're just going to say the area bounded. Very, very important words right there, because when you see area bounded, it's not going to ever be like feet or the accumulation all by itself. Area bounded will always have a geometric interpretation from geometry. So you're going to say units squared. Okay, 3.75 units squared. All right, so now the next one is right Riemann sums for equal subintervals. Okay, we're going to basically go back to this to borrow so we don't have to have the video take so long to watch. And we're going to do, again, 4 right Riemann sums. Okay, so let's go ahead and get started. We have right sub 4, our delta x from that b minus a over n doesn't change, that's still the same. We do have 4 equal subintervals, so it's 1/2. So that's that 1/2. And now we just need these 4 y values, or heights, if you will. Okay? And because it's right Riemann sum, we're going to look at the furthest right ones. Okay? So let's go ahead and take that first, second, third, and fourth. Those are the y values that we're now going to get. Okay? So we'll have 1.25, 2. So 1.25, let me put this in red. 2, 3.25, and 5. Okay? So again, if I go to my calculator, it's basically going to be the same as this, only because we're starting from the furthest right instead of the furthest left. We don't need that 1, and we need to add 5. Okay, because that was that last one on the furthest right, which showed us 5 was that height. So we would multiply all that by 1/2. Okay, so times 0.5, we get 5.75. All right, so 5.75 units squared, because again, this is area bounded. And if you were to look at it like the graph, you would have the over approximation, okay? And just a quick sketch, just so that you could see that, it's going to look like something like this. Right, 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 because there's 4 of them. And you're looking for the area underneath the curve, underneath all that. So that's why you have that over approximation. That's why this number's a lot bigger than the one that we had before. Okay, so this would be an over approximation. Okay, because f of x is increasing and f of x is concave up. And because it's a right Riemann sum, you can see because of those stipulations, you're going to have this extra error that's an over approximation. Okay? All right. Let's go ahead and go to midpoint Riemann sums. Okay, quick sketch. We're going to look at from 0 to 2. And there are 4 equal subintervals, 1/2, 1.5. But the thing is that between 0 and 1/2, this is where the midpoint is going to happen. Between 1/2 and 1, this is where that midpoint is going to happen. Okay, and then you come down. Between 1 and 1.5, right here, that is where the midpoint is going to happen. Draw a straight line, come down. And then, yes, at 1.5, all the way to, because you're looking at 4 equal subintervals, 1.5 all the way to 2. At 1.75, that right here where this x is, that's where the midpoint is going to happen. Okay? So again, the biggest mistake people make with this is that they think that, okay, you still have this 2 minus 0 over 4, which the delta x of each one is 1/2, or 0.5. Okay? That is the width of all of these rectangles. When people do the midpoint, for this first rectangle that I'm going to shade in orange, they mistakenly do the base. They put it as 0.25, okay? And then times the height of whatever this is, okay? it's not going to be 0.25. 0.25 is what you're going to use in order to get what is this y value that I've highlighted right here, or that I've dashed in blue. Okay? So you're trying to do what is f of 0.25 so that you have your y value. Otherwise, your height. Okay? Because remember, area is base times height. Otherwise, the base here times the height of whatever this is. That is what we're going to get. Okay? Where did this 0.25 come from? Because of midpoint formula. Midpoint formula says add the x's first, which in this case is 0 plus 0.5, and divide by 2, which is 0.25. Okay? Now let me show you how ultimately I'd want you to be able to interpret this. We know from this table we have 0.5, so on and so forth. Let me go ahead and rewrite this because I don't want to get you confused. Okay, so you have 5 points. Here's your x's, here's your y's. Now, in order to do midpoint, okay, you need to find the average between those x's. So 0 plus 0.5 divided by 2 is 0.25. Now at 0.25, if I plug it back into the function, okay, so if I plug this back into the function right here, let's see what we get as far as a y value height goes, okay? Let me go ahead and put f of, this is why I stored it the way I did, f of 0.25. We'd get 1.06. 1.063, okay? 1.063 is our rounded answer, but I'm going to go ahead and put up to 6 decimal places while I'm doing this by hand, okay? Or you can use your calculator and just have the calculator just do it all in one shot. And I'm going to show you what that looks like here in just a bit, okay? So, little recap real quick. Our table had 1, 1.25, 2, so 1, 1.25, 2, 3.25, and 5, okay? That's what we had before. This, a lot of people mistakenly try to think that they're doing the average of the y's, like with trapezoidal, and that would be wrong. Notice I never took the average of 1 and 2.5 here for this first rectangle. I took the average of their x values in order to get in between 0 and you could do this if you want visually, in between 0 and 0.5 is 0.25. And the y value that 0.25 spits out, because I put it back into the original equation, would be 1.0625. Okay? So that first area of this first rectangle is going to be a base of 0.5. Okay, that's this jump, not 0.25, but a jump of 0.5, and that's the base times height. And the height is going to look like this 1.0625. Okay? That's the area of the first rectangle. Again, average of the x's. Use that x to put back into the equation to see what your y value is going to be. Okay? So in this case, what we're doing is we're doing f of 0.25. That's my first y value, which is equal to 1.0625. And then we're going to add that with f of 0.75. Okay, so let me go ahead and move this over. And then we're going to just keep adding. So that was here. Now what is f of 1.25? And then last but not least, right here, what is f of 1.75? Okay, GCF'd out. All of these are equal subintervals with the width of 0.5, not to be mistaken with 0.25, and midpoint sub 4 would be what your answer is here. And this, if you're using the calculator, is how you can definitely write down your pieces. If you don't want to write f of 0.25, you're going to actually have to put as far as like, it's best just to write f of 0.25. Otherwise, you're going to have to put f of 0 plus 0.5 divided by 2 plus f of 0.5 plus 1 divided by 2 plus f of 1 plus 1.5 divided by 2, and so on and so forth. But all of those are going to represent what you already have there, there, there. I didn't write that last one, but that's what you would get. Okay? So, let's go ahead and get that midpoint sub 4. Okay? Midpoint sub 4 is going to be control clear. And we're going to do 0.25 with jumps of 0.5. Alright, so f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Now we know this is all going to be GCF'd out, so some of you will even just do this all in one shot. And you're going to do 0.5, not 0.25, times all of that sum. And yes, it is all in parentheses to get 4.6. Let's see what we can round this to. 4.625. Remember, round this to 3 decimal places. Not throughout the problem, but at the very end of the problem. Throughout the problem, remember, it's 6 decimal places. So 4.625 units squared. Because again, this is still area bounded. Okay? So, let's go back. 3.75 was an under approximation. 5.75 was an over approximation, somewhere in the middle. 4.625 is a better approximation. And then last but not least, we will do the trapezoidal. Okay? So, real quick sketch. We have 2, we have 1, we have 4 subintervals. This is 0. The trapezoidal is going to look like this. So from here to wherever that goes, straight line from 0.5 to 1, straight line down. From 1.5 all the way to 1, straight line down. And from 2 to 1.5, straight line down. This looks like it's going to be as close to the actual answer as, because there's very, very little error that's being shown. So 0.5, 1, 1.5, 2. So, again, this one is just the average of the y's. So we will then, to save time, average those, multiply by 0.5. Okay? And then we will average these, multiply that by 0.5. Then we will average these, multiply that by 0.5. And lastly, we will average these and multiply that by 0.5. Okay? So let's go ahead and go to that. We'll have 1 plus 1.25 over 2. That's the average of the y's. This one's easier than the midpoint. It's less tedious. Just don't get them confused with each other. Plus 2 over 2, because these are the average of the y's. And then 2, 3.25. And then 3.25 and 5. So the average of those, the average of these, all of these are going to be added up. and they all have the same width of 0.5. This is trapezoidal sub 4. Alright? So, and then you're just going to put this in the calculator. Okay? Just for instructional purposes. Let me go ahead and do that real quick. So we'll say control clear. Whoops. Escape. Control clear. Then we'll have 1, 1.2. So 0.5 times the parenthetic piece, control divide. Okay? Whoops. And here's we're going to go ahead and put 1, 1.25. So 1 plus 1.25 over 2, because they're the average of that first y value. Okay? And if you need to go back and see how we first did this in part A, the video, to see how we're doing this as far as the average of the y's, please go ahead and do so. 1.25 and 2. So 1.25 and 2. Yep. Let me go ahead and do it like I did the other one. Control divide. 1.25 plus 2 over 2. Again, this is different from midpoint. Make sure that you're understanding what you're dividing by 2 and why, and what you do with that next. 2 and 3.25. Whoops. So 2 plus 3.25. We're going to do that average of whatever that is. And last but not least, we're going to add this last one. 3.25 all over 2. Now, this does feel like a lot of work. Integrals are not this long, okay? This is just like the fundamentals on how integrals work. So when we start doing it by shortcuts and everything, that is like when we did the derivative. When we did the definition of the derivative a long, long time ago, and we had that f of x plus h minus f of x all over h as h is approaching 0, and this is the derivative. All that work that we used to do, and at the very end we plugged in 0, and that was what our derivative was, that little shortcut, like we learned power rule, quotient rule, and all those other things, product rule. That is what integrals will be as far as the shortcut is concerned. The long way to do it, that way we used to do a long way with derivatives, that's what this area underneath the curve with Riemann sums is. It is a little bit tedious, it is a little bit long, but that's basically what it's going to, as far as we need to know how to do it by hand to get the approximate area bounded or accumulation, whatever it is that we're looking for. And we're going to be looking at problems here real soon. All right? So let me make sure 1.25, 2, 3.25, 3.25. Yep. So it is correct. We'll do control enter. And let's see what this is equal to. Just 47.5. All right, so 47.5. Something might be off. That seems a little bit high. Because that midpoint was 4, this was 5, and that was 3. It should not be that high. It should be close to 4-ish. The average. Oh, that's why. That's why. All this needed to be multiplied by 0.5, not by 5. And yes, simple errors can occur like that. But if you have all this written down on the test, you would only miss very little for that 0.5. Okay, so you want to make sure you write everything down. So sure enough, 4.75, which would just move it one to the left, is going to be our answer, units squared. All right.